Okay. So let's start. Right. Uh, where was I? Yeah. So like I did above, I mean, here, what did I get? I got that D is big O of e to the minus A, right? So, or sorry, B prime minus A. Yeah, B prime minus A. So, yeah, so D is big O of e to the B prime minus B prime minus A, which is I mean, it's B prime is within bounded distance of B, right? B prime minus B mod is less than C. So this is a big O of e to the minus B minus A, which is big O of e to the minus T, right? So therefore, the distance between alpha of B prime minus B plus T, that's W, and gamma of T, this is less than or equal to the distance W gamma n of T plus the distance gamma n T gamma T, and this is less than or equal to D, and this is a little o of 1, right? And so the whole thing is big O of e to the minus T plus a little o of 1, right?
Yes.
So that's small as t tends to 0, and so therefore the distance, and this thing is within, if I call this W, then the distance between W and alpha of T is just a constant mod B minus B prime. Well, I mean, mod, it's bounded. B and B prime are functions of T. So B minus B prime, this is less than or equal to C. So that means that the distance between alpha T, gamma T, by triangle inequality, this is less than or equal to distance alpha T W plus distance W gamma T less than or equal to C plus big O of 1, little o of 1. So this is bounded. Okay, that's it. So that implies that gamma infinity is equal to xi. Is this all right?
Yes, sir.
Okay, and for the uniqueness, the uniqueness is rather easy actually. Oh, sorry. Okay. Yeah, okay. So for the uniqueness, we again use a comparison triangle. If I have two geodesics, gamma 1 and gamma 2, so that the distance between gamma 1 T, gamma 2 T is bounded, right? So this is gamma 1 T, gamma 2 T. Okay. And if I fix any S, right? So then let me look at gamma 1 S, gamma 2 S. Okay. So this distance is S, S, and this big distance is T and T. And this distance here, let me call it, say, C. So C is a function of T, but C is bounded, right? So C is big O of 1. Okay, so if I look in this comparison triangle, X bar, gamma 1 T bar, gamma 2 T bar, then I get an isosceles hyperbolic triangle with two very long sides, T and T. So this is T minus S and this is T minus S. So I don't know if I call these points Z and Z bar and W bar, right? And I call these points Z and W. Okay. Then, so this distance is C and this distance I call D, and this angle is theta. Then the same sort of calculation that we did earlier will tell me that this angle sine squared theta by 2 is big O of e to the minus 2t, right? Yes? Is this all right?
Yes.
Okay. So you get this, and then once then you apply this to the smaller isosceles triangle here, and so you get that D will become big O of e to the minus t minus s, right? Okay. It's the same sort of calculation that we did earlier, right?
Yes.
Yeah, so here S is fixed and T tends to infinity. So this goes to 0, right? Because S is fixed. T tends to infinity. Right, so therefore the distance between gamma 1s, gamma 2s, this is less than or equal to D, which is big O of e to the minus t minus s. So this goes to 0 as t tends to infinity. So therefore gamma 1s is equal to gamma 2s for all s. Is this clear?
Yes. Yes.
Okay, so we get a uniqueness of the ray joining any point to the inside. So this is just like Hn, all right? So gamma 1s is equal to gamma 2s for all s. All right, is this okay?
Yes.
Okay, good. So we have this. So now let me, so I did this in a bit of detail, but just to give you an idea of what sort of, arguments we use here. So the other thing we can say is that, okay, so here I need a little bit of assumption that, let me assume that X is a proper metric space. So let me assume X is proper. Okay, well, first let me just talk about comparison angles. So I have geodesics. So now, okay, I can talk about comparison angles at infinity. Okay, so now I take a base point X and I take two boundary points psi and eta. So then I know I have these two unique geodesics, right? From X to xi and from X to eta. So I can take points along these, right? So if I call these geodesics, say alpha and beta, so this is say alpha of t, and this is say beta of s. Okay, so I have x in x and xi eta in boundary x. Okay, then if I take alpha to be the geodesic joining the unique geodesic ray from x to xi, and beta to be the unique geodesic ray from x to eta. Okay, then I can look at the comparison angles at x between alpha t and beta s, right? Okay. Now I know that this comparison angle increases monotonically along geodesics, right? That was a defining, it was a equivalent property of cat -1 spaces, right? That comparison angles increase monotonically along geodesics, right?
Yes.
So therefore, the limit as st tend to infinity will exist, right? Okay. What will this limit be? Because these angles increase monotonically, this will be nothing but the supremum over st, right? Of the angle. Yes?
Yes, sir.
Right? It's easy to show because these increase monotonically, this limit will exist and equal the supremum, right? And this I define to be the comparison angle theta x between xi eta. Okay, so this is the definition. Okay, so this belongs to the interval 0 pi. All right. Okay. Now notice that this function is symmetric, right? So theta x of xi eta is theta x of eta xi. Okay. And it satisfies positivity, right? Because if theta x of xi eta is 0, then that tells me that the comparison angle between by monotonicity, the angle between alpha t and beta t is 0 for all t, right?
Yes.
But if this angle is 0, then that means these are both at distance t from x. So then these points are equal, right? So alpha t has to equal beta t. Right? Because in the comparison triangle, these 2 points, the comparison points will be equal, right? The angle at the vertex is 0. So these two sides are the same. So alpha t bar will be equal to beta t bar. And so alpha t is equal to beta t, right?
Yes.
Because the comparison triangle is degenerate. Okay. So therefore, this is true for all t. And that implies that xi, which is alpha infinity, is equal to beta infinity, is equal to eta. All right. So this function satisfies symmetry and positivity, right? This angle function. Now we want to show it satisfies triangle inequality. So this will actually give a metric on the boundary. All right. So now let me take 3 points. So I fix X, and now, so now I want to show triangle inequality. For theta X on boundary X. So I have 3 points, xi, eta, zeta in boundary X. Okay. So what do? Okay, so let me just, this is getting a bit crowded. Let me move this below. So I join the X to these by geodesic rays. Okay, now I take points along these geodesic rays. Okay. So suppose this is xi, this is zeta, and this is eta. All right. Okay. And so I'm taking points, say, what should I call them? Say U, V, and W. Okay. These are points along these geodesics far out. Okay. And let's say all at distance T. All right. So this distance is T, this distance is T, and this distance is T. Okay. So now what I do is I form the comparison triangles for these two triangles, XUV and XVW. All right. So, and I join them together. I put them together. So I'll get two isosceles triangles joined together like this. I join them along the common edge, X bar, V bar, and U bar, W bar, right? Okay. So this is T, this is T, and this is T. All right. Now, for T large enough, the geodesic from U bar to W bar, it passes through this triangle. So, okay, let me assume that theta x of xi eta is positive. Okay. If it is 0, then we're done. If equal to 0, then theta x of xi eta is less than or equal to theta x xi zeta plus theta x zeta eta, right? So we're done. Okay. Yes. All right. So see what happens when I draw this in H2. In H2, I'll get a picture like this, right? I'll get these two very large triangles. And this angle will be converging to a positive, will be converging to this theta x of xi eta, right? I mean, oh no, actually not. Okay, fine. Oh no, that's not quite true. That's not quite true. 1 second, let me think about this for a second. Yeah, well, I mean, this geodesic will pass through this side. That's the only thing I want to say. Yeah, I mean, well, that's just a property of isosceles triangles in H2. If you put two isosceles triangles next to each other, right, then the geodesic joining this side to this, I mean, this diagonal will pass through the two diagonals will intersect. So I'll think of a proof of that. Sorry?
The convexity of balls in H2. That's
Yeah, that's right. That's right. That's right. Thank you. Thank you. Yes, yes, yes. So, I mean, I know that this distance from the origin and this distance from the origin, this is T and this is T. So therefore, if I go along this geodesic, this will stay inside the ball of radius T. And so therefore, it will intersect this diagonal, right? Is it clear? Because this diagonal goes up to T, right? And so every point on this geodesic is within distance T. So therefore, it will intersect somewhere along this geodesic. All right?
Yes.
Okay, fine. So now I take this point of intersection and I don't know, let me call it, say, P bar. So P bar corresponds to a point on this geodesic here, say P. And now I join by U to P and P to W by geodesics, right? So what do I have? I have that yeah, and I take a comparison triangle for XUW, right? Okay, so okay, fine. So let me call this, yeah, this distance here from U to W. So so this is say U bar prime, W bar prime, and X bar prime, and this distance is say D, which is equal to mod U W, and this is T and this is T. Okay, so now mod so D here, this is the distance between U and W, so that is less than or equal to UP plus PW. And now by the cat minus 1 inequality, this distance UP is less than or equal to U bar P bar. And PW is less than or equal to P bar W bar. But now this is a geodesic in H2. So the sum of these two distances is equal to mod U bar W bar. Right? So therefore, in this triangle, this angle here, if I call this theta, and if I call this, I don't know, alpha and beta, right? Then I have, if I look at this triangle here, X bar, U bar, W bar, and X bar prime, U bar prime, W bar prime, then they both have the sides at the vertex are both T and T here and T and T here. And this side D is less than or equal to this side here. So therefore, this angle theta is less than or equal to this angle alpha plus beta, right? Yes, is that clear?
Yes.
And now as T tends to infinity, this angle theta, this converges to theta x xi eta, and this alpha converges to theta x xi zeta, and beta converges to theta x zeta eta. So that's it. All right. Is it clear?
Yes.
Yes. Okay. So therefore, theta x is a metric on boundary x. So this is one way to give a topology on the boundary, right? You get a metric, so you take the metric topology on the boundary. It's via this comparison angle, okay? But what happens if we do this in Hn? In Hn equal to the ball, and if I take x to be the origin of the ball, right, then this is my ball, this is a xi and an eta. So in Hn, I know that any geodesic triangle in Hn lies in a copy of H2. So any geodesic triangle is equal to the comparison triangle. So the comparison angle is just equal to the hyperbolic angle here, which is the Riemannian angle, which is the same as the Euclidean angle, right? So, so that tells me that this theta x of xi eta is just equal to the Euclidean angle, right? Is that clear?
Yes.
This is Euclidean angle at 0 between xi eta. Okay. So this metric that I've constructed, this is just the angle metric on the sphere, right? Which is the same as the arc length metric on Sn-1, right? So this theta x becomes the arc length metric on Sn-1, right? Is that clear? Right, the angle is just the arc length, right, of the spherical geodesic joining
Yes.
xi, right? Now on the sphere, we also have another metric, right, which is the caudal metric. On Sn-1, I can take the straight line Euclidean distance, right? So how can I express this in terms of theta? Anyone? How can I express this distance in terms of theta? So this angle here is theta, right? So how can I express this? This is, come on, this is a basic class 2 trigonometry, right? This is 1, 1. You have an isosceles triangle. This is theta. What is the opposite side? I don't know which class you learned this in, but whenever you learn trigonometry, class 5 or 6 or whatever, I don't know which class, I don't remember. What is the opposite side? This is 1, this is 1. What is this opposite side? Anyone? What, you can't do this? Yes, anyone? How do you get the opposite side?
Two into sine theta by 2.
Yes, thank you very much. Thank you, thank you, thank you. Yes, I mean, which class did you learn this in? Do you remember?
11, 12, I guess.
11, 12. No, come on, you learned this before. Didn't you do sine theta, cos theta before 11, 12?
Yeah, 9, 10.
So you just, 9, 10, at least 9, 10, right. So that's it. So this is theta by 2. So this thing is half sine theta, right? And that's it. So sine half theta, I mean, sine half theta. So this is 2 sine half theta, okay? So mod xi minus eta is 2 sine half theta. So if I just take sine half theta, then this will be half of this. This is sine half theta x xi eta. Okay. So I get the caudal metric or half times the caudal metric is just sine of half this theta x xi eta. All right. So we can look at sine half theta x for a general cat minus 1 space. Okay. And what will sine half theta be? So first of all, sine half theta x will also be a metric, right? Because sine half theta x of xi eta, this is less than or equal to sine half theta x xi zeta plus half theta x zeta eta. And so you use the addition formula for sine. So this is sine. So sine half theta this into cos plus sine half this into cos, and cos is less than or equal to 1. So this will be less than or equal to sine half theta x xi zeta plus sine half theta x zeta eta, right? Because cos is less than or equal to 1. Is this all right?
Yes.
Okay. So sine half theta is also a metric. So we define this to be the so-called visual metric. On boundary x based at x in x, rho x of xi eta is defined to be sine half theta x of xi eta. So why am I interested in this? Because this has a nice formula in terms of distances. So let me define for you what is the Gromov inner product. Of 2 points. So I have 3 points in a metric space. Okay. And the Gromov inner product of yz with respect to x is defined to be half the distance from x to y plus the distance from x to z minus the distance from y to z. Okay. So why am I interested in this? Because if I'm in a cat minus 1 space, this measures how close, for how long the geodesics from x to y and x to z, for how long they stay close to each other. Because what I'm doing, I'm taking plus here, and a minus here. Okay. So you see, I mean, triangles in hyperbolic space are sort of thin, right? Or in a cat minus 1 space, they're thinner than in H2. So they're sort of thin triangles. So you imagine in the limit, if I make this triangle very thin, what does it become? It becomes a tripod, right? This is the thinnest possible triangle. Yes?
Yes.
So this would be a geodesic triangle in a tree. Now, what happens if I do this in a tree? So I'm taking half of this plus, plus, minus. So here I'll get plus, 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 and here I'll get minus, minus, right? So these two will cancel. This plus and minus will cancel with this plus and minus. And then I'm taking a half of this. So this plus and plus will give me 2 times this distance. So this will just give me the distance from X to this point P, right? Which is exactly the distance that the two geodesics stay together, right? So this Gromov-Wiener product in a tree, it gives you exactly the distance that the two geodesics stay together, all right? Okay. Yes, is this all right? Okay.
Yes, sir.
Fine, yeah. All right. Now, what happens to this? What can I say about this sine half theta? Well, as you've seen already, sine half theta, it comes up in the hyperbolic law of cosine, right? So suppose I take geodesic rays from x to xi, xi to eta, and I call these points y and z. Okay, and so y is converging to xi, z is converging to eta. So I take these distances a, b, c. Okay, and I look at the comparison triangle. So the angle here, theta, is converging to the comparison angle between xi, eta at x. So this is x bar, y bar, z bar. This is a, b, c. So what does the hyperbolic law of cosine say? It says that cos h c is equal to cos h b minus a plus 2 sin h a sin h b sin squared theta by 2. So that tells me that sin squared theta by 2 is equal to cos h c minus cos h b minus a over 2 sin h a sin h b. So the first term cos h c divided by this 2 sin h a sin h b, this will look like what? All of these distances are going to infinity, right? Suppose that xi and eta are distinct, okay? So then this comparison angle is converging to a positive number. So this distance c is going to infinity. So so then this looks like oh, there's less than a minute. Let me stop and just when I come back, I'll just finish this calculation. It's just one line. So let me stop for a second. We'll come back and just finish this. Okay.